going around and introducing yourselves to your classmates probably felt a little bit scary, maybe didn't feel too scary. I want you guys to lean into the tool, the resource that you guys have amongst each other this semester. I was telling my OCHEM 2 class last night, the best way to do well in this class is actually to tutor other people in this class. Whether it really feels like real tutoring or not, I would encourage you to exchange numbers, message each other on Canvas, go to the tutoring center down the hall right after class and spend time working on stuff together. If you feel like the weak link in class, if you feel like you're not understanding stuff right, then having a group of people that you think might be smarter than you gives you an opportunity to explain stuff and have them catch those errors and re-explain it to you to help you solidify it. But I want to go back to the idea of tutoring to understand things. They say that you learn best when you're teaching. And it's true that you might make a mistake while you're explaining something that you're learning to somebody else. But it's that process of trying to put it into words, come up with examples, model the idea that forces you to really solidify connections in your brain. I also recommend that you guys, when you're doing your online homework, write everything out. Even when it's problems that just have you point and click, draw little molecules by point and click, draw it out. That process of using your fine motor skills with pen and paper locks that information in your brain better than just moving a mouse and clicking. So take the initiative to put in the work, to build that group chat, and give yourself the best chance of doing well this semester. Did you guys hear how many people are pre-PA? And I feel like they're all right here. You guys should all get to know each other because you're going to go into the same field. You're going to need to get the same thing out of this class. So use the team you have around you to your advantage and work together this semester. It's hard for me to facilitate that, but one way I try to is with these worksheets. I try to give you guys opportunities to move around, get to know new people, work together collaboratively, and that's just the seed I can plant in class. You guys have to take that initiative outside of class. All right. Trying to think if there was anything else. Oh, my office hours have changed since we met on Monday. I realized I made a couple of mistakes. So that PDF that you guys saw on our homepage, if you downloaded it earlier than today at noon, then it's outdated. This is my most up-to-date weekly schedule. The other thing I wanted to say about this that I didn't in last class is that I know a number of you taking a 5 p.m. class at a community college is because your work schedule keeps you busy all day, which means that my work schedule, having office hours in the day, just doesn't work for you. But you see that I've got a very flexible schedule, so message me so that we can try and find a time to meet that fits in both of our schedules. Deal? All right. Let's get into some material, shall we? I have posted this worksheet onto Canvas. So if you're somebody that would rather download this and work on this on your laptop or tablet, you'll find it in Unit 1. And it's right here above these lecture slides. As a reminder, those lecture slides are a bit outdated. I'm not necessarily going to be doing things that work directly with those lecture slides. But you can download this PDF and annotate it directly if that's how you'd prefer to do this. All right, I want to take us back to the fundamentals. I want to make sure we're all on the same page. Generally, we can say that an atom has two parts. Can you guys name the two parts of an atom for me? Actually, I'm going to take the first part you said, which is the nucleus. I want to point out another thing. I have unique ways of writing notes on the board. I like to use arrows to indicate like headers and subheaders. I do try to put notes on the board that is useful for you to copy down into your notes. But you might want to modify it. Maybe you don't like arrows and you want to use bullet points or stars or whatever. But I do try to be thoughtful throughout the semester. So if I ever make some weird mistake on the board, just call it out. Ask me if I can clarify it better. Our nucleus is one part of the atom. This is positively charged because it has those protons and neutrons, which gives a net positive charge. And it has all of the mass. That's not true, is it? Electrons have some mass, and they're not in the nucleus. But the mass of an electron compared to the mass of protons and neutrons, insignificant. So our nucleus is one part of the atom. What's the other part of our atom? Orbitals is a good way of describing that other part, or it's a more technical way of describing it. But we usually call it our electron cloud. And we're going to talk about orbitals, so this is a good time to remind you about it. This is where we find our electrons, and this is what makes up the size of an atom. Was I giving you guys the analogy on Monday? That if an atom were the size of Colorado, the nucleus would be the size of a basketball, and the electrons are just swarming that basketball in the state of Colorado? That's huge, right? The electron cloud is mostly empty space, but that's what we consider to be the size of an atom. Nucleus has all of the mass. Electron cloud has all of the atom. Let's talk a little bit about ions. What makes something an ion? What makes a chemical species an ion? Britton. I like your idea of saying that you can have a molecule that doesn't share electrons evenly. Can we put into words what needs to be true about those species that we can refer to them now as ions? Not all atoms are ions, but some atoms are ions. True? We can think of neutral species. We can think of ionic species. What needs to be true for a species to be ionic? I'm putting this really vaguely as if there's a specific answer, but I'm happy to play around. Brenna? It has that charge. So ions have charges. Why? Fewer or more electrons. We could say the number of protons does not equal the number of electrons. And I think what Kirsten's getting at is that you can't change the number of protons. That's locked for the elements that you're looking at. But you can change the number of electrons. Electrons are more or less easy to donate to a species or easy to pull away from a species. So we can easily change the number of electrons to change the number of protons, to change the charge. Great. All right, and then compare for me molecule versus compound. You know what? This is why I'm not very happy with this board. I know, I don't know. It just seems too small for me. Do you think you could define the difference between a molecule and a compound? Are they similar? Are they different at all? Are they just two different things? Kirsten?
Well, I think, correct me if I'm wrong, a molecule is a combination of different atoms to create like a new thing, and a compound is a combination of molecules.
What do you guys think? A molecule is a combination of atoms. Compound is a combination of molecules. Britton's saying no. Maybe something different. What do you think might be wrong about that idea?
I know, like, sodium chloride would be a compound, I believe, as well as an ionic compound. Molecules, can't think of why.
Would you say that sodium chloride, you said sodium chloride is a compound, an ionic compound. Would you say that sodium chloride is a molecule?
Molecules form
So is
covalent
it
bonds.
like all molecules are compounds, but not all compounds are molecules?
Actually, I think that is a good Venn diagram to build. All molecules are compounds, but not all compounds. No, actually, sorry, don't draw that. I have a definition. No, not necessarily. Actually, I do have something to say to that extent about, you guys know that saying, all squares are rectangles, but not all rectangles are squares. There is a Venn diagram like that, but it actually isn't this. It's not molecules nested inside of compounds. I didn't mean to make that mistake. Also, am I saying your name right? Is it?
Yeah, it's Kirsten.
Kirsten. Good. Thanks. Jordan.
Aren't molecules, they are covalently bonded, or compounds have ionic bonds?
So in this analysis assignment that I'm going to have you guys do all semester long, analysis of an organic compound, does that mean that I don't want it to have any covalent bonding if molecules have covalent bonding but compounds don't? Is that what you said? It's hard, right? These definitions are not things we've ever really written down. They're just words we use a lot, but we don't think about the rigidity of where these definitions lie. Selena.
Is it that compounds are made up of molecules, like singular ones?
Oh, well, I think that's what Kirsten said, right? Which is compounds, molecules build up into compounds. I don't think that's true. I think we could say, look at this molecule of CH4, or look at the CH4 compound, and either of those would be perfectly acceptable. Here's what I'm going to say, unless anybody else wants to pitch in.
Aren't compounds when we put elements?
There you go.
But then molecules when we put atoms together? Is that different?
And I think you're not necessarily describing a difference between them, right? You're just kind of saying two different angles. A molecule is when you put atoms together, and a compound has different elements put together.
So they are the same, basically, but different.
They are distinct enough, and yet they overlap. Yeah?
Is it dependent on the type of elements put together?
Sometimes.
Like hydrogen and carbon?
Let's do Jordan and then Ju.
Well, isn't like, because you can have an oxygen molecule, right? So isn't it just the smallest form of something? So an oxygen molecule would be two oxygens, right? O2.
Mm-hmm.
That would
But you
be a
can't have-
compound because it's just oxygen.
Good. You can have a molecule of oxygen, O2, but you cannot have a compound of oxygen because it's just one element. Ju, do you want to add to that?
Is this similar for compounds, like a fixed ratio?
Compounds are a fixed ratio. I think in molecules we can say they can have a fixed ratio. Yeah, a compound of methane has a fixed ratio of carbons to hydrogens. Yeah. So roughly, to put some words to it, molecules have multiple atoms, often covalently bonded. I don't know what it is, but I think my handwriting has gotten worse over the years. I'm going to say often covalently bonded. Maybe it is that it's always covalently bonded. But what is a covalent bond anyways? Actually, there's a good question. What's a covalent bond? Sharing electrons. It's actually right in the name, right? Covalent. Like co-piloting, you're both piloting the plane. So what is valent? Valence electrons. Those of you in my Gen Chem class might remember that we discussed the Greek root of the word valence actually comes from power or strength. And that's because valence electrons do the chemistry. All of the other electrons are core electrons, and they are inert. They're not forming bonds. They're not being taken or added to or lost. Valence electrons are added to, are lost. Valence electrons are used in forming covalent bonds. Compounds have multiple elements. Covalent or ionic. I like to hit on that because those are words I know you guys know. And yet it opens a blind spot in our fundamental understanding of chemistry, right? I know you know them, but they're really confusing to get a hard definition for. Okay, cool. Moving through this, let's talk about organic molecules and compounds. Who remembers the definition of organic chemistry? Actually, it's a little bit more than just carbon. Organic chemists might not say that diamonds are carbon. Are organic. It is just carbon, but is it organic? It's a bit of a debate. Hydrocarbons. And their derivatives. Good. So, the first activity that we have on our worksheet, group the following compounds. In this case, actually there is one chemical on this list that is not a compound. Ha ha ha, my bad. So group these molecules into their respective categories. Along the top, you'll see organic and inorganic. And along the left, you see molecule and ion. I want you guys to work together for the next 5 minutes or so and try to decide which of those reagents, which of those chemicals are considered organic molecules and which are considered organic ions, which are considered inorganic molecules and which are considered inorganic ions. I don't have a definition for you of inorganic. What is inorganic? Everything else. If it's not a hydrocarbon or its derivative, meaning if it doesn't have carbon, hydrogen, and other stuff, it's inorganic. All right. Next 5 minutes, I'll round us up when we're done.
What was your name again?
No, but that's a good question. A hydrocarbon just needs one hydrogen. Yeah.
Is anything with hydrocarbons like
Is that one?
Can I ask you about this one?
H2O molecule.
Where's the hydrocarbon?
So it'd be an inorganic molecule.
Mm.
So their derivatives.
Derivatives
Still
still
has
have
to
to have
include a carbon.
hydrogen and carbon.
Got it.
Yeah. Or at the
So it's a hydrocarbon or like.
a derivative would be like this, where it's not just hydrogen and carbon, but it has more in addition. That's a good question.
Like C5H5N would also be an organic molecule.
Yeah.
Because it's carbon as well. Okay.
And it has no charge.
Yeah.
And how do you know it has no charge?
Because it's covalently bonded.
Yeah, and there's no metal that's listed.
So.
It's interesting, right, that water is not organic,
Yeah.
because what does life need to exist? Water.
It is.
But it's definitely the most important inorganic chemical to life.
So
I guess that's arguable.
that would be the same thing for organic and inorganic ions as well. NaOH would be inorganic because it doesn't include carbon.
Good job.
Okay.
Natalie, do you want to work with Britton and Vivi to collaborate?
So sulfur.
Where'd Dylan go?
We went to get some water.
Boring.
And that has a different
So you're just doing this alone?
Doing, yeah, I'm done. I mean, he's done too. We just did it. But
Okay.
Yeah, just think the organic ones, the ones that has carbon mostly, right?
Yeah, 'cause they're
And
Yeah.
how we can like differentiate. things.
Nailed it. Did you guys collaborate at all?
Yeah.
Good.
We just kind of talked about needing a carbon for it to be organic.
Good work.
Thank you.
No clue. Leans onto something. Charges. Oh, you know what? Charges don't always have to be shown. Charges can be implied.
So how do I know?
Good question. So it comes down to the metals. If I have a metal and a non-metal, they share electrons. They don't share electrons. The metal will give up electrons completely to the non-metal, which means a metal and a non-metal gives an ionic compound. So by looking for the metals in these chemicals, we can label those as all being ionic. Then we look for the hydrocarbon. Is that what you were thinking, Lean? You've got metal, non-metal, metal, non-metal. On the right track.
I'm just taking it right here.
Oh,
What's it? H2SO4 is an ion. I don't know what it is.
okay.
I think he has a pretty good argument.
I'm curious to hear it. Your argument about
I
H2SO4.
think I forget the name for these kind of things. It's called polyatomic ions,
Mm-hmm.
and they have their own charge. So
You know what else is a polyatomic ion?
oh, NaOH.
OH. Sorry, just OH is a polyatomic ion.
I would put them in ionic compounds.
So I think what I'd tell you to focus on is what about sodium to hydroxide makes it ionic? It's the metal to the non-metal. Is hydrogen a metal?
No.
It's in the same family as sodium.
But it's like an outlier.
It is an outlier. Despite being a group 1 element, it's not an
Big brain.
it's not an alkali metal. You remember group 1 is alkali, group 2 is alkaline earth, and helium technically would be group 2 because it has 2 valence electrons. Helium is definitely not an alkaline earth metal. It is a noble gas. Hydrogen technically is an alkali metal. It's also technically a halogen because it needs just one more electron to get a full valence shell. So the argument is is there a bond between hydrogen and the atom in the molecule of sulfate? Or is it covalent or is it ionic? And how do we determine that?
Well, wouldn't the hydrogen bond to itself?
No,
Never mind. Don't listen to me.
I won't. No. Don't take it like, don't.
You can join.
No, they actually bond to the oxygens. Yep.
I think so.
Yeah? You got a question on it? Close. I would disagree about these two.
Those two.
Thionyl chloride and sulfuric acid. We'll talk about it.
Put them as inorganic molecules.
Yes. Where would the ion be? What would cause an ionic bond? We'll talk about what makes that distinction. Well, so for this, I can see why you would think that, but you shouldn't do that. If you did, why not do it to this? Why not do it to that? Just get rid of the hydrogen. And this actually doesn't have a hydrogen, right? So what hydrogen would you be getting rid of to make it an ion?
So you would do this up here, this here.
I would.
Okay.
Well, we will, absolutely. How do you guys feel? You made a lot of progress.
Yeah. I've been sorted.
Oh, I see it. Okay.
Yeah.
You were worried to mess up the
Yeah.
box.
I only want the right answer.
Understood.
For the molecule and ion, does this mean separating each compound from a covalent and an ionic bond?
Yes. How can you identify whether there's an ionic bond or whether there's no ionic bond, right? That's what we have to answer.
And then as far as inorganic and organic goes,
Okay, so it just depends. Okay, so
You're looking for that,
this first one's ionic. Or carbons and hydrogens together.
right? Essentially.
As long as it's carbon, then it's still inorganic.
Sometimes, yeah. You know carbonate?
For sure ionic.
Carbonate, CO3, 2-. Major component in your bones, seashells, chalk. It's considered inorganic because there's no hydrogen there.
right. So most of the time, if there's a carbon and a hydrogen present,
Like they usually both have to be present together.
It's got to be, well, no, just in the molecule. It's got to be a hydrocarbon molecule.
So they could be separate as long as they're both.
It's a debate, and actually this is a good segue for me about why these lines in the sand don't really work, but they're what people try to go with. All right, are you guys ready? What I heard going around is that the biggest challenge is first, how do you know whether something is molecular or ionic? How do you know whether it has covalent bonds or has ionic bonds? First of all, some compounds have both, correct? Let's take, for example, sodium hydroxide. Sodium hydroxide, super common reagent to see throughout general chemistry and organic chemistry. Sodium being present in the chemical formula and nonmetals being present in the chemical formula tells me that there will be such a strong pull on the electrons that sodium will lose them completely. This is metal plus nonmetal. Look for that metal and recognize that it's going to be ionic. But the hydroxide has a covalent bond. Oxygen and hydrogen share electrons unequally, and we're going to talk about that more in section 2 next week. They share electrons though. So if we were to draw the Lewis structure for sodium hydroxide, we would show sodium with a positive charge separate from hydroxide with a negative charge. It was the presence of the metal that told me that there were charges inside of this species. That's it. That's the only indicator that you really have. And we'll review this a little bit more in depth next week, but it comes down to the difference in electronegativities. The difference in electronegativity between Na and O is above a certain point. And that point was arbitrarily decided by chemists a long time ago. And the difference in electronegativity between O and H is below a certain point. So we have drawn lines in the sand to say that this difference in electronegativity is what we'll call ionic. This difference we'll call covalent. So sodium hydroxide, no carbons, cannot be organic, and it has ions. It must be inorganic, an inorganic ion. All right, so as a reminder, anytime that you see OH, I want you to see a covalent bond. It would have been wrong for you to draw it like this. Why? Now you've broken the OH bond. You looked at that species and thought that it was sodium ion, hydrogen ion, and oxide ion. That's not how it behaves. That's not, its properties don't follow this. When you see the OH bond, I want you to see it as that covalent bond. I'm saying this now, early, because it becomes very important at the end of the semester. So lock it in. Then the other challenging part was simply deciding whether something is organic or inorganic. This is another line in the sand decision. There are some weird instances that I think are interesting debates. Carbonate, CO3 2-, has no hydrogen. So technically inorganic because it's not a hydrocarbon, despite the fact that it can be derived from organic compounds. So it is a derivative of hydrocarbons, but it itself is not a hydrocarbon. This really rides the borderline of whether it's organic or inorganic. Similarly, bicarbonate and carbonic acid. Carbonic acid doesn't have a bond between H and C. Carbonic acid has OH bonds. So is it a hydrocarbon? Well, it does have hydrogen and carbon in the structure. And to my understanding, most people would consider carbonic acid to be organic. But we as humans have tried to put these lines in the sand. We've tried to create these boxes for nature to fit into. And nature doesn't really like fitting into neat little boxes. Nature is a spectrum. And so we're going to run into some instances this semester that really blur the lines between what definitions we should call things. We just have to be comfortable with that sometimes. These molecules, for the most part, are actually pretty easy. Don't really ride the borderline much. All right, so let's group these. Sodium hydroxide, what did you say? Give me a raise of a hand. Britton. Inorganic ion. Water. Raise of hands. Calvin. Inorganic molecule. How many of you put water as an organic molecule? Just a few. You think of organic and you often think of like biochemistry, biology, organic things. And when you think of living things, you often think of water. So that was me intentionally trying to pull your attention to say water not a hydrocarbon molecule, inorganic. All right. CH3OH, methanol. I'm not going to let you guys go twice, so this is going to go really slow if you don't raise your hands. Camilla. Organic molecule. That CH3OH. Remember that OH is a covalent bond. So OH means molecular, not ionic. There's no metal in that chemical formula, can't be ionic. NaOCH3. Hamza.
Organic ion.
Organic ion. We've got that organic structure. In fact, the only thing that's changed here is replacing the hydrogen in the chemical formula with the sodium, right? Now I have a metal, and so I have enough of an electronegativity difference to actually cause an ionic bond to form. But I still have that hydrocarbon group, that CH3. This is what we call sodium methoxide. KOCCH3 3. Yes, good job, Allie. Annie, sorry. This is my chance to practice your names. This is what we call potassium tert butoxide. We're going to talk about it a lot, and I'm going to get you guys more familiar with these names later in the semester. Hydrocarbon, definitely. Ionic, definitely. It's that potassium that tells you it's ionic. SOCl2. Dylan? Inorganic molecule. This is a compound called thionyl chloride. It has a very interesting structure. I'm going to have you guys draw it in a little bit. And thionyl chloride is a chemical reagent we'll use in reactions later in the semester. No carbons, no hydrogens, no metals. It's all nonmetals, so it's molecular, inorganic molecule. Br2. Jew?
We put it outside the box.
Outside of the box? No, it fits. It goes in one of the categories. But tell me why you think it's outside of the box.
Oh, we said, I was thinking about like compounds.
Mm-hmm.
Molecules we were talking about earlier. Said it would just be a molecule.
And it is a molecule. I made that mistake because up here I put the following compounds. I should have said chemicals. Put the following chemicals into the respective categories. But one of our boxes is molecule. If I had put compound here, then Br2 definitely would have to go out of the box. But Br2 does fit our definition of molecule. It has to have multiple atoms. And Br2 does have multiple atoms. It just doesn't have multiple elements. It is inorganic. And that's because, it's a molecule because the two bromines are bonded to each other. This is what we call elemental bromine. You guys might remember that from the periodic table, there are several elements that are diatomic in nature. If you start at element 7, nitrogen, and you make the shape of a 7, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, those are your diatomic elements, plus hydrogen. So bromine, elemental bromine, Br2, molecular. Same with O2. H2SO4, this one caused some debate. But now that we've looked at some others, do you guys feel like your answer has changed? Where does sulfuric acid go? Are there metals? No. Hydrogen is in the same family as sodium, but hydrogen is an outlier in that family. Hydrogen technically should also be a member of the halogen family because it has some similar characteristics to halogens. It needs one additional electron to fill its octet. Sorry, to fill its outer shell. Hydrogen's not a metal. So can it be ionic? H2SO4? No. Are there carbons? So what are you waiting for? Where does it go?
Organic molecule.
Inorganic molecule. Now, I think what most people were remembering about this is that sulfuric acid readily deprotonates twice. It's a strong acid twice, and it forms sulfate ion. Good. That's a good memory to have. But this dissociation of sulfuric acid into sulfate and 2 hydrogen ions, this happens in solution. That happens in water. It doesn't happen on its own. The hydrogens are actually bonded to the oxygens in sulfate. And we should think of those as covalent bonds. All right. And that's actually not true. The H plus never exists. It bonds to water and it forms H3O plus. But that's for another day. We're going to talk about acids next week. CH3CO2H. Good job, Carla. This is acetic acid. Do you guys know another name for acetic acid? Vinegar. You all have worked with this at some point in your life, I promise you. NaNH2. Inorganic ion. Good job, Perla. This is sodium amide. Sodium amide is another reagent we're going to deal with this semester, so I want you guys introduced to it early. Lastly, C5H5N. Kirsten? Organic molecule. Earlier, you guys were asking if we were going to talk about some of those topics that you had questions on. Did we answer them? You feel confident on looking at a chemical formula and deciding, is it organic, is it inorganic? Is it ionic, is it molecular? What questions still linger? And we won't run into the exceptions much, and I promise I won't stake your grade on the exceptions. That's just not fair. Okay, let's take a break, shall we? Let's do 5 minutes and come back just before the 3.
You have in the blender bottle.
Protein,
Nice.
chocolate.
What's your protein of choice? There's only one right answer, so don't.
I have whatever my partner buys.
Oh, okay. What does the bag look like?
It's a red bottle.
Red bottle.
It's like a gallon tub.
Yeah, okay.
Yeah. Boy, I have no idea.
I'm kind of kidding because I just really like just ingredients. I don't know.
What is the right answer?
Just ingredients.
Mm.
Yeah.
I thought you were saying you know the ingredients, but you don't know the brand. The brand is called Just Ingredients.
Yeah. I want to say it's a Utah-based company too. So support local.
Is that, do they make the protein bars too? And the cover of the protein bag, or the cover, the wrapper, is like the ingredients list. 2 eggs,
so.
1
Oh,
cup
that's,
flour.
I'm jumping in on your conversation. That's RX bar.
Yes.
You're right, RX bar.
Thank you.
Ingredients is good.
So yummy, right?
Yeah, I really
Try
like
it.
their strawberry.
Oh, all right, I'll look into it.
Actually, also their snickerdoodle flavor. Because they have like
Snort
just
straight protein
big-
powder.
That's so out of pocket to say. Just, what did you say, simple and
They have like the pink Starburst one. Have you tried that flavor?
Yes.
That flavor's so good.
It's like a fruity.
What is the flavor? Pink Starburst.
The blue
Like
one's
the bag is pink and it has like pink Starburst.
I've heard like everyone raves about it.
It's so good.
Is it like your safe protein powders?
I think it's
No, like,
I've never had this much of a conversation about it, and I drink these every day.
I just got back from Europe and they like don't drink protein.
But they just don't drink water, so.
They don't they drink coffee and that's like it. But I went to Starbucks in Switzerland and I was like, can you guys do the protein lattes here? And they looked at me.
I would look at you like that too.
I've actually never heard of a protein latte.
At Starbucks?
Well, I don't drink at Starbucks.
No, you can get protein lattes and you can get protein cold food.
But I've never heard of a coffee shop doing that. They've got protein on hand? You sparked a big conversation, Dylan. We're still talking about it. You ever had a protein latte? Right, apparently. Huh. Selena, you spell your name with an S?
We do.
Okay.
Well, I don't spell it. I didn't name myself. Yet.
Yeah. But,
Unless
I mean, like, you, yeah.
your best student, even though I won't be the best student.
What?
You could name me your best student.
Oh, that's a long name. I'd rather stick with Selena. Unless you have another one. But your best student, I'm going to be referring to you as your best student, which is a mouthful. Okay, your best student, get on the board and show us what you got.
1 plus 1 is 2. That's all the math we'll do in this class.
No, we'll do a little bit more, but pretty much. We'll do like 12 plus 3 is 15.
But like nothing like nothing like Chem 2.
No algebra. Just calculus.
Calculus.
No, I'm just kidding. I do like calculus, though.
How much math did you take?
I had to take up through Calc 3. But I considered taking differential equations and intro to abstract math because those two classes would have given me a math minor.
Wait, I have to go right now. I was like,
Boy, I expect great things this semester.
I'm gonna bring you Principal Yates protein powder next time.
Oh my goodness. Okay.
what do you usually drink?
No, whatever my partner is buying. I've never looked at the name on
Don't
the.
know what the packaging looks like?
It's a red tub with a black lid.
Is it like whey powder or is it like?
He doesn't know.
I make it every day.
Have you ever made a ninja cookie?
Take a look.
Like the ice cream, the protein ice cream?
What'd you call it?
You have to use a ninja cookie. So that's really good.
Huh. No.
Really good.
Never heard of this. You guys are opening my mind to things I could have never imagined. All right. I want to teach you guys the ABCs of bonding. You may think that you know your ABCs of bonding, but sometimes I feel like you need a refresher. So the second table that we're going to fill in, we're looking at all of the different ways that you can bond some of these atoms and make different charges. So the first thing that we need to cover is the equation for formal charge. You may have been taught an equation for formal charge, but I'm going to teach you one that I think is a little bit more effective and a little less convoluted. Formal charge is equal to the number of valence electrons for the atom you're considering. That means that every time you calculate formal charge, it's on a case-by-case basis. You look at a specific atom and you calculate its formal charge. Minus the number of dots plus lines. Dots represent represent non-bonding electrons, and lines represent two bonding electrons. The equation that you're normally taught for formal charge is take the valence electrons, subtract the number of non-bonding electrons, then subtract half the number of the bonding electrons. Which means you have to do the gymnastics of looking at a line, remembering that it represents 2 electrons, and then taking the number 2 and dividing it in half to get 1, which is where you started when you said it was one line representing 2 electrons. So when you have a Lewis structure, we're also going to learn how to do bond line structures. You look at that structure and you just count all of the dots individually, and you count all of the lines individually. It's the easiest math you'll do all semester. It's some of the only math you'll do all semester. And you've got the formal charge. So let's go through and look at valence electrons for these common atoms we're going to be doing. Carbon, nitrogen, oxygen. What am I representing by X? Not everything else. Halogens. Fluorine, chlorine, bromine, and iodine. That's what we represent with X. X for us is our halogens. How many valence electrons for carbon? 4. Nitrogen? 5. Oxygen? 6. Halogens? Good. You're recognizing that periodic trend, right? As you move across the periodic table, the number of valence electrons increases. We also will look at some trends when we build this table. On the left-hand side, I've mapped out that we're going to put bonding forms that have a +1 charge, bonding forms that are neutral, and patterns that are giving a -1 charge. So I'm going to start us off looking at carbon in a neutral state. This is another downfall. I've got the other classroom I usually teach in. My projector goes right on the board, and I can just have this right on the board. Yes? Not really. It just doesn't work well. Yeah, I've tried it. It's too much. I don't like it. I'd rather do my ink. All right. Carbon neutral needs to have 4 bonds, or 3 bonds, 1 dot. So to make that happen, I can draw carbon with 3 bonds and 1 dot. There is another way to do it where it has 2 lines and 2 dots, but it's just not a common situation that carbon finds itself in. And I did say on this, we're looking at the more plausible combinations, the ones that happen the most often. So this is a radical species. It has 1 unpaired electron, 1 dot, 3 bonds, 3 lines. Neutral carbon. I could also have carbon with 4 lines. Do all 4 lines need to represent different bonds? Definitely not. I could also have a situation where carbon has 2 lines in one direction, a double bond, and then 2 other single bonds. That's still 4 lines. That's still a neutral carbon. I could also have a carbon that has 1 line in one direction and a triple bond in the other direction. There's another combination where carbon has 2 double bonds. These are all neutral bonding patterns for carbon. As you move across the periodic table to the right, those atoms prefer less bonds and more electrons to themselves. As they become more electronegative, as they increase their valence electrons, they need less shared electrons. They want more lone pair, non-bonding electrons. So you'll notice that these bonding patterns for neutral carbon are shared. Oops, I went the wrong way. These are the same bonding patterns that you'll see in a positively charged nitrogen. Nitrogen with 4 bonds has this positive charge. And so all of those same bonding patterns we saw in neutral carbon represents a positively charged nitrogen. A negatively charged carbon represents a neutral nitrogen, represents a positively charged oxygen. You're going to start seeing these trends in these bonding patterns. The reason I say this is because you will have test questions that give you a structure and ask you to predict the missing formal charges, if any. But on top of that, sometimes you'll see structures that don't explicitly say where the charge is. And I want you to get familiar with those bonding patterns so that you can quickly assess where the charges are. I want this to feel like your ABCs of the structures. So I'm going to give one example for each of the neutrals. Actually, I think what I'll do is I'll give the radical example and then one normal example so you don't have to do any radical situations. Nitrogen as a radical, when it's neutral, has 2 bonds. Oh, 2 bonds, a lone pair, and 1 unpaired electron. Most of the time that you see a neutral nitrogen, it will have a lone pair and 3 bonds. Oxygen in its neutral state likes to have 1 bond with 1 radical, or oxygen likes to have 2 bonds, 2 lone pairs. We're not going to deal a lot with radicals, which is why I don't want you guys to have to try and predict radicals in these different bonding patterns. But I do want you to be aware of radicals, unpaired electrons, because they will come up later in the semester. Halogens. Now you could pick a halogen to represent here, or you could represent all halogens by just drawing X. Halogens will either have 3 lone pairs and a radical, or halogens will have 3 lone pairs and a single bond. Those are neutral bonding patterns. I would like you guys to spend the next 10 minutes in your groups. I gave you all of the different combinations for neutral carbon. I want you to find any other possible combinations for neutral nitrogen, neutral oxygen. I'll give you a hint, there are no other neutral halogen combinations. And then I want you to start figuring out what do you need to do to make these other situations. And remember this trend that you're going to find. A neutral nitrogen is a negative carbon, is a positive oxygen. Whatever combinations you came up with here, replicate them, but change the atom. Don't do the radicals. Work in your groups. Brainstorm as much as you can. I'll be coming around to help you guys get over any hurdles you run into. Good. Yeah, you can ignore those instances of the radical. Good, Britton. Can you show your positive charge?
Oh, yes.
Show those charges so you don't forget that's what we're representing.
It is like that, right? With the brackets and the plus.
If you want to,
Learn, I don't know.
yeah, I think in our class we're going to be more specific about where the charge is.
Okay.
So kind of like I did on those nitrogen species.
I didn't know that's what that was. Okay.
Yeah, a little positive charge
Just like right
in
now.
a circle.
Okay, thank you.
Oh, wait, we can't put radicals? Is that what you said?
Don't do the radicals.
Oh, so like that is the radical, so I should.
Right. So like you picked this species to replicate here.
Oh,
You did, right?
Yes, I did,
Two
yeah.
lone pairs and a dot. So you can ignore that. Instead, replicate this here.
oh, okay.
And
So should I cross that out? Or?
no, I think actually you could turn that into a line.
Oh yeah, you're right. Okay.
Then, just like we did with the nitrogen, show that that oxygen is holding a positive charge by just putting a positive next to it.
Oh. Do you do that for carbon too, or?
Yeah, that carbon that you have there has a positive charge. Good work. So Auriel, I'll have you, Aurelie, thank you. I'll have you ignore the ones with just one dot.
Okay.
And so instead of doing this one here, let's do this one. And you can fix that by just turning that into a line. Do you know what I mean? Perfect. You got it.
Okay, thank you. Yeah, because I guess it's bonded to different things.
Layla, I think you meant to draw nitrogen there.
Oh, sorry. Too true. Too true.
Easy mistake. Good work. Nice. Now, draw that positive charge next to the nitrogen in each of those cases. And if you want to, ignore that radical species.
This one?
Yeah, the radical is the one electron that's not paired. Yeah, ignore it. We're not going to see those very much.
Okay, so question. With this one, you kind of give us the options and then said we have all these different ways, like a triple bond here. Is it kind of the same here where
Yes.
I'm ignoring this, but we could have a triple bond here or a double bond and a single bond?
Those are all perfect.
So like as long as you have the lone pair, like the bonds can go whatever.
Any
situation.
combination, any possible combination
Okay.
is doable.
Okay.
You nailed it.
Are we missing any though?
Nope.
Oh, okay.
That's it. That's it.
Let's go. Perfect. Okay.
Okay, so we just put
Yeah. Looks great. Here, I would say, don't forget to keep adding that positive charge next to your atom to show that it holds a positive. Same thing here, we'll put a positive charge next to the nitrogens to indicate that they are positively charged.
Is there another configuration for oxygen that we're not getting?
Yes.
What is it?
Well, in addition to the radical version,
Oh, I see. Okay.
why do the single bonds need to be going in separate directions? You didn't get my other three versions of carbon either. So there's three other ways that these bonds can come. There's one other way that these bonds can show up.
And it's just up there on the board.
Those three are the other carbons.
Okay, I see.
But I just got you started here.
Yeah.
I want you to,
Well, I know, but see your oxygen category?
yeah,
I'm missing the one that has just the single valence.
yeah.
Or the single dot.
I don't know why.
No, I don't either. That's
Just
what
copy it down.
Yeah.
And then there's one other form that works. So if we are replicating these, yeah, this one looks good.
But I didn't do a line.
This one actually needs another line. This bonding pattern is this bonding pattern, yeah? And then you'll put a positive charge next to this, and once you fix that, you'll put a positive charge next to that.
So all these ones on the top row are gonna have.
That's right. They'll all have a positive.
It does work. Hell yeah. That's what I thought. Or I think that we did. But I guess it does biggest brains. They might have slowed
Okay, I know that wasn't a lot of time. And it was a strange assignment, wasn't it? Have you ever tried to figure out all the different ways that those atoms can bond?
All the time in my free time.
Yeah, Dylan, you and I should hang out sometime. Only when I'm at work, though, because that's,
Maybe if it's hot yoga.
I'm just doing this at work.
Is there a difference between blue and red, or you're just trying to?
Yes, the difference that I'm showing between blue and red. Red are radical species, and my understanding is that some of you may not have a good understanding of radicals. I don't think that in my Gen Chem 1 course we talk about radicals except for briefly with nitrogen species when doing Lewis dot structures. Can anybody define a radical species? Define a radical?
You just said so many things radical.
Doesn't it? Doesn't it just have one free electron, and so it makes it very reactive, right?
Yeah, it can be very reactive. So radicals are that unpaired electron and how do you represent an unpaired electron? It's just a dot, right? And in general, radicals are highly reactive. Free radicals in biology are things that generally you don't want interacting in your body. Notice that a lot of the radicals show up in the neutral lane. Radicals don't have to be charged species. They can be neutral species. I did tell you to ignore doing radicals in the top lane. And then I remembered that in Unit 3, I'm going to have you draw some of those radicals. Some of those radical cations with a positive charge. So I think it is useful for you to see what those radicals look like. So I want to point out again the connection between these lanes. Let's look at this negatively charged carbon. 3 bonds, 1 lone pair. Those can be 3 single bonds, a double bond and a single bond, or 1 triple bond. All 3 of those bonding patterns are what give us neutral nitrogen. 3 bonds, 1 lone pair. All of those bonding patterns are what gives us positively charged oxygen. 3 bonds, 1 lone pair. The further to the left you go, the less those electrons prefer sharing electrons. They're more stable when they have more electrons to themselves. We can see the same thing with this positively charged halogen. If it's got 2 bonds and 2 lone pairs, it's positively charged. That's what gives us a neutral oxygen. 2 bonds, 2 lone pairs. That's what gives us a negatively charged nitrogen. 2 bonds, 2 lone pairs. So these patterns repeat themselves. You'll notice that we never break our octets here because most of the time in organic chemistry we deal with species that stay within an octet. One of the outliers in this whole category is right here. That X minus is on its own. None of the others have that bonding pattern of just having 4 lone pairs. And then we've got this outlier up here, which is carbon with a positive charge. You'll notice that those carbons have 3 bonds. That's it. This is the only one without a full octet. No, that's not totally true. The radicals technically don't have a full octet either. But I do want to point that out to you guys. Up there, that positively charged carbon has 6 valence electrons around it. We're going to deal a lot with those types of carbons this semester. So I'm introducing them to you early so that you can get familiar with seeing carbon with only 3 bonds.
When it does have that positive charge on top there, can you see that in a triple bond?
This is a great question. I almost drew it and then I erased it because this bonding pattern doesn't really happen. It's plausible. We can theorize it. It's not one you're going to have to deal with. So I'm not worried about you guys getting familiar with it.
Okay. So like rules for this then, like I was able to draw most of them because I know that you said like, oh, follow the trend. But apart from that, I wouldn't be able to pick one and just say these are the most plausible arrangements and these ones aren't really likely, even though like mathematically it matches up. You know
True,
what I'm saying?
true. If you take this table while you're preparing for your final exam at the end of the semester, or we can do the final exam next week if you guys want. Just kidding. But isn't it crazy how quick the final will come? Take this table when you're studying for the final, and you'll realize that you have started to recognize a lot of those bonding patterns. You're getting more familiar with why those charges show up when those atoms are bonded the way they are. So this is just an introduction. I really don't expect this to make sense to you right now. But I might recommend that you go home this weekend and try to replicate this table from memory. And then look back at the ones you got right, the ones you got wrong, the ones you missed. And then next week, try to replicate this from memory again. Think about the ones you got wrong, the ones you got right, the ones you missed. As you do that more and more, you're going to get more familiar with these bonding patterns. It will become easier for you to spot one of these atoms in that bonding pattern and know what charge it has. That's what I'm trying to get you to recognize, is the relationship between bonding and charges.
Yeah, I had a question about the oxygen and the +1.
Yeah.
The blue,
Yes.
why is that the same as the 0 but with a positive charge?
Oh, you know what? That's a good point. It's wrong.
Okay.
That's why.
Because, like, I don't understand why that one's different.
You are totally right. What I should have done was this.
Yeah, that's okay.
2 bonds, a radical, and a positive charge.
Sorry, thank you.
No, thanks for pointing that out, Kirsten. I had this one drawn incorrectly. I didn't have enough bonds going to it, and I should have had one less lone pair on it.
I was trying to circle all of the blue ones. I was like, I don't have that one, but that doesn't make sense.
Yep, you nailed it. There was one other document I want to point out to you guys on Canvas. Right at the top of each unit, you'll find this document called the Learning Objectives, LOs. This is my way of making sure that we cover all of the important things. And it's my way of putting into words what I want you to be able to take away from each section in each unit. So, section 1, relate formal charge and bonding patterns. We've done that now. You know these bonding patterns and you know what charges should go with them. Do you know what we haven't done? We haven't sat down and applied this equation, but I guarantee that if you sit down with each of these bonding patterns that we've drawn and you plug it into that equation, they'll give you that +0 negative charge that you're expecting. That's a good foolproof way of making sure that you've drawn your structure correctly and labeled your charges correctly. But if you familiarize yourself with these bonding patterns, it becomes second nature. That's the fastest way to recognize charges in structures. I want to spend a little bit more time today looking at our next component, which is valence bond theory. which essentially gives us Lewis structures and hybridizations. We'll be able to get started on this. We're going to have to pick up with it next week. And then we will wrap up this worksheet next week as we move into section 2. So valence bond theory tells us that bonds exist, atoms are held together, because orbitals that hold these electrons overlap. And now an electron pair is able to span both of these atomic orbitals, or these hybridized orbitals. So now the electrons are able to be held between both nuclei, because their orbitals create a pathway for the electrons to move between both. This has its benefits, it has its flaws. We're going to talk about another bonding theory next week called molecular orbital bonding theory. But I want to give you guys the rundown on atomic orbitals and hybridized orbitals, just in case you've forgotten them. The atomic orbitals that we'll be dealing with the most are the s orbitals and the p orbitals. There are 3 p orbitals. These each lie along a cardinal axis. So we can call them px, py, and pz. Do you guys know what orbitals are? It's where the electrons are found. Do you want to add anything more to that? Good. Orbitals have shape, orientation, and size. You can describe those 3 features using math. Orbitals are mathematical equations that describe the shape, size, and orientation of where you will find electrons. Orbitals are math. If orbitals are math, that means that you can add orbitals together and subtract orbitals from each other. You can do math with that size, shape, and orientation. So these orientations, s being fully spherical, and the p orbitals lying along the cardinal axis, lying along the cardinal axes, they don't set themselves up well to have minimal strain during bonding. If an atom with these orbitals tried bonding with another atom, there'd be a lot of angle strain between all of the groups. So an atom can hybridize its orbitals, create new orbitals with new sizes, orientations, and shapes that helps minimize strain during bonding. And we're going to look at the 3 most common. What happens when sp hybridizes? What happens when s and 2p hybridize? And what happens when s and 3p's hybridize? Notice that s is always hybridizing. That perfectly spherical orbital, it's not of any use to an atom. So it will hybridize it with these linearly aligned orbitals and create new things. The rule is the number of orbitals that get hybridized must equal the number of hybridized orbitals. S and p, 2 orbitals in, 2 orbitals out. They're not s anymore, they're not p anymore. We call the new orbitals sp. These are the two orbitals of sp. They look pretty round like S, but they've got a second little nub like P. By the way, the shading and the unshading, it just represents a positive charge at the beginning of the math equation, or not charge, a positive sign at the beginning of the math or a negative sign at the beginning of the math. The shading just helps us convey that the math is saying different things about how the electron is moving. You'll notice that these two orbitals are aligned linearly. That's because they have consumed only the px orientation. So these sp orbitals, two of them, only have orientation along x. An atom that is sp hybridized has these two sp orbitals, plus it has its unhybridized py and pz. These orbitals will be used for different things. Hybridized orbitals give us sigma bonding. Unhybridized p orbitals give us pi bonding. When s and 2p come together, what do we call the orbitals? Yeah, but we don't call it sp squared. sp2. When I have hybridized both px and py, I have access to an entire plane of geometry. The x-plane, the x-axis and the y-axis gives me the xy plane. So these orbitals look a little bit more like p. They've got a larger nub on the other side, but they are now spread out in 3 directions across a plane. We get 3 of these, plus we have 1 unhybridized p orbital. An atom that is sp2 hybridized can make 3 sigma bonds, but only 1 pi bond. I'll let you guys go from there. We'll pick up with sp3 on no class Monday, huh? Martin Luther King Jr. Day. So no class Monday, class on Wednesday. We'll pick up with sp3. We'll look at Lewis structures, molecular orbital theory, and then we're going to get into section 2. Have a good weekend. I'll see you guys in 1 week. Yes.